Health, Psychology and Human Nature with André Sturesson. Hey friends, hope you're having a great day. Are you following me on Instagram and Facebook? Please go to Health, Psychology and Human Nature on Instagram or Facebook, or both for that matter, to get the latest episodes, inspiration and more. Please take a pause and go there. Also, if you like the episode, please share it with a friend, family member or somebody else who you think might like it. Welcome back, friends, to Health, Psychology and Human Nature with me, André Sturesson. A science-focused podcast where we explore, learn and improve our lives together. Mitochondria are often referred to as the powerhouse of the cell. They are important as they create energy which enables us to live our daily lives. Mitochondria also seem to affect other stuff like our health, aging, diabetes, and more. But how can we affect our mitochondria? The answer is exercise. Professor David Bishop, he's a world leader in muscle exercise physiology with more than 250 publications. And he also leads the Skeletal Muscle and Training research group, which has two key areas: exercise as mitochondrial medicine and human performance. His Twitter handle is @BlueSpotScience. Friends, I really hope you enjoy the episode. David, welcome to the show.
Thank you. I've been listening to your podcast to get ready, so I've enjoyed it. So I'm really pleased to be here and to chat.
Perfect. Yeah, really looking forward to it. I'm glad to. I heard you listened to a little bit of the Martin Chabal episode.
Yeah, that was probably the one that's closest to some of my research, but I want to get to some of the ones on mental health and well-being as well. So I'll try and get to those later in the week.
Yeah, sounds great. All right. I think that, you know a lot about mitochondria and you've been doing a lot of research about mitochondria as well. And I think for those that have never ever heard about, mitochondria and have no idea about what it does, perhaps we could just start off, by just talking a little bit about mitochondria, what mitochondria is.
Yeah, I think the classic description you'll see in the textbooks or on the internet is the energy powerhouses of our bodies. So basically in every cell of the body, we have these mitochondria which are producing the energy that you need for everything that you're doing during the day. So, the people who are listening while you're sitting there listening and your heart's beating, the mitochondria are producing the energy that your heart needs, that your muscles need, that your respiratory muscles need, etc., to keep you alive.
Right. So it's pretty much like the main energy source that we have to be able to do everything that we do.
Yeah, probably 99% of or more of our energy comes from these little powerhouses that you find in every cell of the body.
Right, interesting. And from my understanding, mitochondria has its own DNA, right? It's kind of an own organism as well.
Yeah, I think that part of it is really interesting in the history. So it only has a very, very small its own mitochondrial DNA. So it's most of the information to make new or to build mitochondria comes from the nucleus. But they're unique from other cells in that they have their own little mitochondria, their own small DNA, which produces some additional components of the mitochondria.
Right, interesting. All right, so you mentioned that mitochondria it makes like energy for us to be able to do all the stuff. Does it do anything else except for that?
I think if you read the classic description, like as I said, it'll describe their energy producing role. But increasingly, we're finding that the mitochondria do have other roles related to aging. They're also involved in producing reactive oxygen species, and they're also involved in what's called programmed cell death, which is if there's a cell which is dysfunctional and needs to be removed, they also have a role there. So even though they're most famous for energy producing, they also have a number of other roles which are important to maintain good health.
Interesting. So, like, why would you say why would you say that mitochondria is important for our health, well-being, and everything else?
Well, I think obviously, producing energy is a pretty fundamental task as well. So, I mean, without energy, you're not going to be able to move your muscles, to breathe. Yeah, you'd you die in a few seconds if you weren't.
That's a bad thing.
If you weren't producing energy, so I think that definitely sort of underlies the importance. But
yeah.
Even if we don't understand completely why, having well-functioning mitochondria has also been linked to a lot of diseases, so things like diabetes, for example, but also things that you might not necessarily think about, so things to do with the brain, so even Alzheimer's and dementia, and there's a huge range of diseases that have been linked to mitochondrial health. So maintaining our mitochondria as healthy as we possibly can is important not only for health, but also, as I said, maintaining daily function. And then if we go a little bit more to the extreme, I guess, to endurance athletes that need to produce a lot of energy to perform at their best, it's also going to be important for endurance performance. So right from an ordinary person who needs to maintain a healthy lifestyle up to elite athletes, the mitochondria seem to be critical.
That's interesting. So it really seems to have a lot of different roles. So it seems to be really, really important for us in our everyday lives, but it also seems to be important when it comes to Alzheimer's and diabetes, and even the athletes as well. So it seems to have affect us in many ways.
Yeah, and as I said, I mean, I think in some ways it's not that surprising considering how fundamental having an efficient and adequate supply of energy is going to be to the function of every single cell in the body.
Yeah, for sure. And from my understanding, also you can also affect your mitochondria with exercise. And I think that is something that you've been doing a lot of research about.
Yeah, and I think that's I think for me it's fascinating, and it's been occupying the last 10 or 15 years of research. But I think if you think about a muscle, if you use your muscles, then they'll get bigger, and if you don't use your muscles, then they'll get smaller. As in, if we're not active or as we're aging, and you can think of the mitochondria in exactly the same way. If you challenge your mitochondria with the right type of exercise, they can get bigger and work better. If you're inactive or get sick, and also with aging or certain diseases, then you'll find that the mitochondria will get smaller and won't function as well.
Interesting. So, like, what would you say if you would like your mitochondria to get bigger, or maybe I'll ask that also. Is it that the mitochondria get bigger, or is it that you get more mitochondria if you do, ordinary cardio like jogging or bicycles?
Yeah, it's interesting because it's such a basic question, and it's one that we still don't have a great handle on. Because if you imagine, mitochondria are in this 3D space in your legs, and we kind of take one-dimensional or two-dimensional pictures of these mitochondria. So it's kind of hard to tell exactly what's happening, but it seems to be that it's probably that it's more that the mitochondria, when they're challenged, they expand and get bigger, more so than increasing the number of mitochondria. And so if you I guess if you see the classic, someone does a search on the internet and you look for a classic picture of the mitochondria, you'll see them as these little oval shapes which are sort of dotted around the muscle. In reality, they're more like, I guess, worms sort of plowing through your muscle. And so what you can have is that these worms will get longer and fatter, more so than having a greater number of the mitochondria.
Ah, that's very interesting. Okay, so it's more that just like the muscle gets bigger, the mitochondria also, also get bigger when you're exercising. That's pretty cool.
Yeah, and I sort of don't want to get too much into the technicalities, but I think that's where, if you imagine you've got this worm kind of growing through your muscle. If you're sorry about that image, but but if you chopped through the muscle, you could chop through this longer worm in a number of different places. And in a 2D image, it would look like there was more of these discs in the muscle, but it's actually just that you've cut through this longer worm in more places. And so that's why I'm saying it's difficult with our sort of imaging techniques to know exactly whether there's more mitochondria or just longer, bigger mitochondria. But at this stage, I think most people would suggest that the predominant way that the mitochondria adapts to exercise is increasing the size and the length of the mitochondria network.
Interesting. So, like, if you would try to affect the mitochondria to get bigger mitochondria by exercise, like, what would you suggest? What kind of exercise is the best?
Yeah, and I'll just I know we spoke about this before we got on the air, but I guess the other aspect is, if you can imagine this energy powerhouse in your muscles, and there's two main ways that you can affect them. So one is you can make the mitochondria bigger, so you're increasing, you're having a bigger energy powerhouse in your muscle. And the second way is you can keep that mitochondria a similar size, and you can make it more efficient so that same mitochondria can produce more energy. Right. And obviously you can have a combination of the two, which is bigger and more efficient mitochondria that produce more energy.
Right. Okay, so those are two ways. And like, if you would like to, okay, so they can get bigger, or they can stay the same size, and then like their performance, even though they're smaller, can increase. But if you would like to, like, try to get them bigger, like, what do you do then?
Yeah, sorry. Yeah, and so that brings it to that point. So what we're finding, I mean, anytime you stress the mitochondria, and in this case with exercise, they'll respond by adapting so that next time that same exercise stress shouldn't be as stressful. And so any type of exercise will, any type of aerobic exercise specifically, will increase the size of your mitochondria. What our research suggests, though, is that the total volume of exercise is critical to increase the mitochondria. So we see that the more exercise you do, in terms of, you can think about it, number of minutes of aerobic exercise, the greater the increases in the mitochondrial content.
Right. Okay. So the more volume, is it also like a law of diminishing returns? So like that like if you would exercise 100 minutes or 150 minutes per week, that you will get a lot of, like, that your mitochondria will grow, and then if you do like 500 minutes, that they will grow, but they won't grow as much, or?
Yeah, a really good question. And I don't think, I think one of the challenges is a lot of the research that we and others have done, because it's with muscle, you need to look inside the muscle, so we do muscle biopsies, is it tends to be on, at best, moderately trained and sometimes even well-trained individuals. We don't often get a look at elite athletes.
Right.
So, but in the studies that have been done to date, there doesn't seem to be a lot of evidence for a plateau. So basically, the more aerobic exercise you do, the greater the changes in the size of the mitochondria. I suspect, though, that you're right, that there will come a point where there will be a plateau, and there's also presumably some point to there's a limit to how much mitochondria you can jam into a muscle.
Yeah. What do you think? Like, let's say. No, another thing that I'm curious about. So if you're doing like you're jogging or you're going with the bike, at what level is the best when it comes to what level is the best for your mitochondria to exercise at?
If we're talking about, as I said, mitochondrial, the mitochondrial size,
yeah.
What we're seeing is that we think it's the total volume of exercise, and the way I think about the total volume of exercise is the number of minutes times the intensity. So if you did, for example, 30 minutes at 80% of your VO2 max, then that would be sort of similar to 60 minutes at 40% of VO2 max. That would give you the same volume. So in a roundabout way to answer your question is, I would say, the combination of intensity and duration that allows you to do the most amount of exercise. So if your intensity goes too high, then that's going to limit the duration that you're able to maintain at that intensity. Whereas if the intensity is too low, then you'd have to do a super long duration of exercise to be able to get the same effect. So I said there's still this still needs to be resolved. But I would suggest if you chose an exercise intensity probably around about your sort of lactate threshold that you can then maintain for quite a long duration, that I would think would be pretty close to the sweet spot for trying to maximize the increases in mitochondrial size.
Interesting. So what does that mean, the lactate threshold?
Yeah. So what I'll try and describe it in this way. If you go out for a slow jog or slow bike ride, and when you initially start off, there'll be an intensity which you feel is pretty comfortable, and then if you start increasing your intensity, you'll find that it gradually gets maybe a little bit more difficult.
Yeah.
But there's a point where a small increase in your speed makes a big difference in how hard the exercise feels. And so that's what we talk about is the lactate threshold. And I think most people have probably experienced this, and even people who are just sort of casual exercisers will know that when they go for a run or a bike ride themselves, that intensity that goes from being pretty comfortable to this is quite difficult, I can only probably keep doing this for 5 or 10 minutes. There's that threshold which we talk about is called the lactate threshold, which is that threshold between moderately difficult and becoming quite difficult.
Right. Like, is there any way of knowing that you're at the right level as somebody who has never heard about this stuff before? You
can, I think, some of the, even though it can be quite complicated, some of the the simple ways I think work quite well. If I was working with an athlete, we could bring them into the laboratory, and we could test them, and we could find out quite precisely where that point is. For someone who's like a casual exerciser just looking to get some health benefits, probably the talk test works pretty well. So if you think of you're exercising with a friend, and you can talk comfortably to them while you're exercising. If you go a little bit faster, you kind of have to say a few words and then take a deep breath and catch your breath and then say a few more words. And if you're in that zone, you've probably gone above your threshold and you're starting to exercise at too high an intensity. So I think if that point where you can still reasonably comfortably hold a conversation is probably a good guide.
Interesting. I think, yeah, I've heard about that a lot. Like a lot of people talking about when it's like when you got a problem talking to somebody, that then that seems to be the level. But I was also interested to know. Okay, so for an everyday person, like let's say that you do the recommended 150 minutes of like jogging or bicycling a week, like how much of the mitochondria benefits are you getting at that point, do you think?
I think especially sometimes the good thing if it's someone who's starting exercise is that's when you're going to get the most gains.
Yeah.
So I'd say for sure, if you're going from sitting on the couch to doing 150 minutes of exercise per week, I'd expect that that would be sufficient to initially get some improvements in mitochondria. What would be important though is that as you get fitter, to either increase the duration or increase the speed of that exercise to maintain the improvements in the mitochondria.
Interesting. That is something that I haven't really heard. Okay, what did you say that if you have to keep on improving to be able to hold the benefits for your mitochondria?
To get the greatest benefits, yeah. And I mean, we and others have seen that, and I guess it's exercise physiology textbooks, it's referred to as progressive overload.
Right.
And what that means is that the body is responding to a stress. And so when if you go for a 30-minute jog at an easy pace, initially that's going to be a stress on the body, on the muscles. And so the muscles will respond by adapting. But if you keep running or cycling or rowing, whatever your exercise choice is, but if you keep running at exactly that same pace and exactly that same duration every day, that becomes less and less of a stress on the body, and it becomes less and less of a stimulus for adaptation. And so you're going to start to get some diminishing returns. And so, as I said, in our field, it's referred to progressive overload, and what that means is very gradually increasing the stress so that you continue to stimulate your muscles to adapt.
But is it that you don't keep on improving, or is it that you actually that your mitochondria also actually becomes smaller?
We've seen that the mitochondrial size seems to be maintained quite well. If you stop and do nothing, then you're absolutely right, because then the mitochondria are no longer being stressed, and they no longer need to be functioning at as higher a level because they don't have this stress of exercise. So there, over a few weeks, you will gradually see the mitochondria return to their pre-levels.
Right.
The positive thing, though, is that it's normally in almost any physiological adaptation in the body, it's a lot easier to maintain it than it is to get the gains.
Yeah.
So sometimes, if you're doing a lot of exercise, initially you will get your improvements in your mitochondria, and so that might be, say 5 days a week. Once you've got those gains, it's easy. You're able to probably maintain those gains on maybe 2 or 3 times of exercise a week. But if you then go from 5 to 0, then you will see, as I said, the mitochondria will think, okay, I no longer need to be as big or as efficient, and they'll start to return to what their pre-exercise condition was.
Interesting. So like if you would do let's say that you would do cardio 5 days for let's say 2 weeks, and then you would just do 2 to 3, do cardio 2 to 3 times per week. After that, then you would keep the benefits, or
you should be able to keep most of the benefits, and there may be a slight decrease, but yeah, almost most of the physiological adaptations I've seen, it's a lot easier to maintain them than it is to actually improve or increase that quality in the first place.
That's interesting. So perhaps people should, do 1 week of 5 times, and then you can do 2 or 3 times for a couple of weeks, and then they'll have these, more intense exercise weeks every now and then.
I think the important message out of that, which is a good practical message, I think, is that the consistency and forming a good habit is critical. And I remember on your other podcast, Marty Gabala spoke about that as well. And so, you sometimes see people who will, do these boot camps and do super intense exercise for a week or 2 weeks and then return to doing nothing, and you'll get this kind of seesaw effect. Whereas if you can, get into a regular habit and each week doing a little bit of exercise, then ultimately that'll allow you to get some gains and then to also maintain those gains.
Oh, that's really interesting. And I know that you also been focusing, I think you've been focusing on athletes as well. If you would really try to optimize the mitochondria for someone, what does that look like for an athlete, for example?
Yeah, I wish I had the answer to that. But
Yeah.
I think I'd be very popular, and I'd be getting lots of calls.
Yeah.
I think we're definitely moving closer, and one way I like to think about it is if you can imagine the healthy diet pyramid, where you have carbohydrates and proteins and fats and everything, in a balance to try and get the best nutritional gains. And so I kind of think about a similar model for the mitochondria, in that instead of nutrition, you could replace that with different types of exercise. And if we're talking about the mitochondrial content, then that's more the base of the triangle.
Yeah.
So that's where you need a high volume of exercise, so lots of minutes at a moderate intensity to increase the size of the mitochondria. As I said earlier, the mitochondrial function, or how efficient the mitochondria are at producing energy, is also important. And what we and others have also seen with our research is that that's where the very high intensity type exercise seems to be important. So either high intensity interval training, which might be for a few minutes, or even sprint interval training, which is where the classic is people might do 30 seconds, 20 or 30 seconds all out, followed by a few minutes rest, and then 20 or 30 seconds all out. And then maybe even some, lower intensity interval training in the, moderate to high intensity interval training. So I think, by hitting these different types of exercise, we feel, that hits the mitochondria and provides different stresses to the mitochondria. So that way you can increase both the size of the mitochondria and also the function of the mitochondria.
Interesting. So it's kind of like proteins perhaps is doing the steady paced cardio like jogging, and then you have perhaps the let's say fats or the carbs is more doing the sprints, the high intensity stuff instead. So it's like kind of two different things in a way.
Yeah, and I think there's when I describe it, I guess it's sort of a little bit distinct. I think there's a little bit of overlap there as well. So I mean, even with the very high intensity interval training, you can get some improvements in the mitochondrial size as well. So I think it's not there's not sort of one exercise that only increases the mitochondrial size and a different type of exercise that only increases the mitochondrial function. But I strongly believe that getting those, both of those together will lead to the greatest mitochondrial adaptations with exercise. Yeah. And I think the cool thing is that it matches really nicely with what elite athletes do. So, elite endurance athletes tend to do, around about 70 or 80% of this low to moderate intensity continuous exercise training, and then maybe 15 to 20% of quite high intensity interval type training. So I think elite athletes need, there's more than just having good mitochondria to being an elite athlete. But I think over hundreds of years of trial and error and experimenting with their own training programs, elite athletes have come to a similar approach, which is, I think, consistent with what our research is showing.
That's very interesting. But perhaps we could talk a little bit about the other part, then the high intensity stuff. So you mentioned that when we do this kind of sprint exercise, then it seems to be affecting how well the mitochondria perform, and perhaps not the size. Was that what you said, or?
Yeah, and even some of Marty's stuff has shown that you can get increases in mitochondrial size with the high intensity exercise. But what we've especially our research group has shown is that the very high intensity exercise is more effective at improving the mitochondrial function. So you can imagine that even if the mitochondria don't increase in size, they become more efficient and better able at producing the energy that our body needs.
Right. Like let's say that you would do 3 of these sessions a week. So perhaps you do 20 seconds, then you rest for 2 minutes, you do 20 seconds, you rest for 2 minutes, and then you do 20 seconds again. And each time you exercise, you do really all in, you do all out on a bicycle, for example. How much of an effect do you think that would have on the mitochondria?
Yeah, so even with just a few weeks of exercise training, we've been able to see a 20-30% increase in mitochondrial function that we measure in the lab. So that type of exercise can definitely be very effective at improving the function of the mitochondria. And I think, as I said, I think if you're then able to mix that with the occasional more classical, longer duration aerobic training, I think that would probably give you the best overall changes in the mitochondria.
Interesting. But how, Is it do you hit a plateau here as well? Like, let's say that you would do sit every day, for example, or you do this kind of intense exercise every day, like 5 days a week or 7 days a week. Like, would it be a big difference between that and doing 3 times a week, or?
Yeah, with the function, I think we don't really know, but I think most of we see most of the physiological systems. Ultimately, there is going to be a plateau, and I think I guess the classic example is probably with weightlifting, and it's a good one because the mitochondria are inside the muscle, so it's a bit difficult for someone to look in the mirror and see if their mitochondria are changing. But with weight training, you've got that visual confirmation, and there's obviously a limit. If you look at professional bodybuilders, Mr. Universe, those type of people, there's eventually you will reach a limit in which you can't increase the muscle size anymore, and the same is definitely going to be true with the mitochondria. That we don't know exactly where that point is, but there's going to be a point where even with continued training, you're not going to be able to further increase the content and function. But I think for most of your listeners, I'd say that they probably don't need to worry just yet about reaching those limits.
Right. It would be very interesting also to know like what your recommendations would be. So let's say if you're a 30-year-old, for example, and like you would like to you would like to exercise regularly to affect your mitochondria in a good way. It doesn't have to be athlete level, like perfection, but that I would like to affect your mitochondria in a good way. Like, what would a good schedule be for a week, would you say?
Yeah, so if I was, so let's just say, assuming they've got 5 days, 5 days in a week to be able to work on this, I would be probably looking at 3 days of sort of classical longer duration endurance exercise, and maybe 2 days of high intensity interval training. For the endurance training, I'd be looking to, anything is good, but trying to gradually increase the intensity and duration, and I guess increasing the duration up to whatever your weekly schedule allows. So it might be a 30 to 40 minute exercise session at that talking that talking pace that we spoke about earlier, and then mixing that with a couple of interval training sessions. And again, I think one of the beauties of interval training is that there's almost an infinite number of ways that you can do it to try and keep it interesting. But for an example, I'd be looking at doing maybe 2 to 4 minute work efforts at an intensity that you can maintain for that whole session. So if you're starting your interval fast and kind of gradually getting slow towards a lot slower towards the end of the 2 or 4 minutes, then you're probably going a little bit too hard. So I'd be trying to do the intervals at an intensity that you can maintain reasonably constant for the duration of the interval. And typically I'd be looking at what we talk about is a 1-to-1 work to rest ratio. So if you're doing 2 minutes of exercise, I would then have 2 minutes of rest. If you're doing 4 minutes of exercise, I would have probably 4 minutes of rest. And so in that way you can, as I said, you can play around with the general concept, so that basically every time you do an interval training session, it's going to be slightly different.
Interesting. So would you say, like, if you start with the endurance, you said that like 30 to 40 minutes, like in a talking pace. Would you say that so that is that a good amount of time per session? Would you say?
I think our research would suggest that the more exercise you can do, then the larger the changes in the mitochondrial size. But I think the public health recommendations, as you said, are typically 150 minutes per day, and most people struggle to do that. So I kind of start with feasible. But if you're someone who's been doing exercise regularly for a while and you're able to fit 60 minutes or longer into your day, then I would predict that you would get better adaptations from that. But again, when we're talking about what happens when you stop exercising, I'd rather see someone consistently do 30 minutes a day, for months after month, than do 1 week where they do 60 minutes a day and then have a month off before they get back into it again. So I think it depends obviously on people's on lifestyles. I think if you can do 20, 30, 40 minutes a day, that's great. If you're able to cope with, and also your schedule allows a longer duration, then I would expect you would see greater increases in mitochondrial size with more training.
Right. I was also thinking about like a combination. So let's say that you were doing like 40 minutes of biking, for example, or sitting on a aerobic bike at the gym. And then after that, you do some like 20-minute sprints, for example, for like 20 seconds sprints, sorry, seconds, not minutes, like 3 20-second sprints with like 2 minutes break. What do you think about that combination of doing both what do you think about that combination?
Yeah, to be honest, that's some of the next research we want to do, is exactly, trying to get the recipe right, how to mix different types of exercise. So in theory, it makes a lot of sense, but I'm not aware of any literature that has looked at that. There are some studies that have alternated those types of training, so doing long duration endurance training on one day and then the next day doing some form of interval training. And from my reading, they typically produce some of the best adaptations in aerobic fitness. So I think the theory is definitely excellent, and I guess we've also got one of the great contributions of the Swedish language, fartlek training, as well. And so, but we don't know there. I mean, that may also be a good approach. So for people who aren't, familiar with fartlek, and apologies if I butcher the Swedish translation of it's speed play. So doing your you could tell us what fartlek means.
Exactly. Fartlek. So that is, from my understanding, it's basically that it's kind of doing intervals, right? Isn't it?
Yeah, I think my understanding, I could be wrong, is that I think it's a Swedish word, but I think it kind of the literal translation is speed play, or playing with speed, or something like that. So what it is like if you're going along, and if you're doing just jogging, and then I know classically you've got those the power poles beside the side of the road or some other marker. You might just every now and again do a 20 or a 30 meter sprint at a very, very high intensity. So it's just I guess it's a way to make long endurance runs a little bit more interesting, and also to increase the stress of the exercise. So those sorts of what you're talking about there, I think those sort of combinations in theory make good sense, but at the moment we haven't. I'm not aware of research that has looked into that.
Interesting. So it would also be very interesting to know, like, you yourself, when it comes to your exercise, like, what do you do for your mitochondria?
Yeah, I think I try and follow the research a little bit, but also I guess my personal training isn't just focused on my mitochondria. So I'll normally have a bit of strength training and stabilities training and that weaved in there. So I typically will alternate between the two. So one day I'll do a more aerobic focused training, and then the next day I'll do strength or stability training.
Right.
And with my endurance training, I normally alternate between more duration focused, and then another day I'll do some of the types of intervals that we've been speaking about. And I think I said until we've got the perfect answer. I like the kind of it's like a finance term as well, the diversified portfolio. So
yeah,
trying to use different types of exercise to stress different parts of the body to get the best all-round health adaptations.
For sure. I was also interested to know, you mentioned before that you shouldn't be doing intervals at the level where you get slower, like towards the end. It would be interesting also to know. So like, at what level should you do the intervals? Could you talk a little bit more about that when you do the 2 or 4 minutes at intervals?
Yeah, and I try. Hopefully, I don't want to confuse anyone. So sometimes with the intervals, we'll have what's called sort of high intensity interval training, but there's also sprint interval training, and so if you're doing sprint interval training, that's when you're going to do 20 or 30 seconds all out.
Yeah.
And with that type of training, absolutely, you're going to be slowing down throughout those 20 to 30 second intervals. There's no way that you can go flat out from the beginning for 20 or 30 seconds and not slow down. It's just that, physiologically that's impossible. So if you're doing those type of sprint intervals, then absolutely you will be slowing down. If you're doing what I would refer to as high intensity interval training, that's the slightly longer intervals that I was talking about. So 2, 3, 4, even 5-minute intervals. And as I said, I think if you choose an intensity that you can maintain for the duration of those intervals, I think that it's a pretty good way to make sure that you are choosing a high intensity, but an intensity that's not too high to get the best adaptations.
Mm. So it's even. So is it worse for your mitochondria, or do you get less of an effect if you push too hard?
That we don't. Again,
right.
Again, we don't know. But we've got some really cool results that we haven't published yet. But we saw that when you do sprint interval training, that some of the mitochondria get damaged, so they get a little bit swollen, and they're just, when we look at them in the images we take of the muscle, you can clearly see that they're damaged, and we see around about 15% of the mitochondria seem to be damaged. And I guess what we don't know is that whether that damage is good and it's important to stimulate the mitochondria to adapt, or whether it could potentially be a negative adaptation. And again, if we use the strength training analogy, we know that when you do strength training, there can be these sort of micro tears in the muscle, which appear to be important to stimulate the muscle to adapt. So what I can tell you is that we don't see any of this damage with low to moderate intensity training. So I guess that's my only sort of caveat.
Yeah.
Is there potentially with the very, very high sprint interval training, there may be some damage to the mitochondria, or that we do see some damage to the mitochondria. What we don't know is that whether that's actually a good and important response that stimulates the mitochondria to adapt.
Right. Interesting. One thing that is really interesting is that if we do the jogging at the continuous pace, or if we do this more of this high intensity exercise, that it seems to affect the mitochondria in different ways. Like, why do you think that is?
Yeah, I think because it's interesting, and I love having conversations with people like yourself who ask these really fundamental questions. And one of the really fundamental questions which we still haven't answered is what exactly is the stimulus that causes the muscles to adapt.
Yeah.
But what we think is that it's the changes in the environment of the muscle which are important for the adaptation. And so if you think about, I'll give you a really simple example, is if you do a really long exercise, so if you think about a marathon, a couple of hours for the elites and obviously a lot longer for the less elite, whether you're elite or less elite, you'll often hear athletes talk about hitting the wall, which is when their muscle is depleted of muscle glycogen. And so that's going to be, when you're doing really long duration endurance exercise, you're going to be depleting your muscle of glycogen. And that could be an important signal that tells the mitochondria to adapt in a certain way. Whereas when you do really high intensity exercise, something that's going to be different, and most people will be familiar with the term, I think, is lactic acid. So when you're doing high intensity, you've got that burning sensation in your legs. That's going to be a lot higher when you do very high intensity exercise. So that may be a stimulus that causes the mitochondria to adapt in a different way. And that's is getting a bit technical, but that's what our lab is really interested in, is trying to decipher those signals. But I think even if we don't know exactly what the exact signals are, I think you can understand that different types of exercise are going to cause the environment in the muscle to adapt in different ways, and that's then going to lead to probably the different mitochondrial adaptations that we see with different types of exercise.
Interesting. So like from an evolutionary point of view, it's perhaps that. So like if you're doing a lot of let's say intense hunting, for example, that you need to sprint a lot, then we have this kind of adaptations to be able to handle those kind of situations. And if you're more of a I don't know, like chasing animals on the safari, for example, for hours, then perhaps we needed those kind of adaptations to be able to hunt properly or something. What do you think about that?
Yeah, no, I think you're spot on. And I guess, ultimately, what we think is, the whole idea of adapting to exercise is that so that the next time that same exercise is going to be a little bit easier.
Yeah.
So, if you think about, again, I'll use a weight training example. If you pick up a large weight and it's really heavy and you have to, grunt and strain to lift it up, if you keep doing that, your muscles will increase in size and will get stronger. So the next time you go to lift that same weight, it will actually be a little bit easier.
Yeah.
And the same, as you described really well, the same analogy with the mitochondria is that the mitochondria will adapt so that next time you're doing the marathon or the high intensity exercise, whichever the mitochondria have been exposed to, the mitochondria will adapt in a specific way so that the next time that specific exercise will be easier for the person or animal to be able to do.
Yeah. It's just fascinating how, like, the more episodes I do, the more I become fascinated about, how good we are at adapting for kind of everything. It seems to be one of the key things for us humans.
Yeah, and I think and there's lots of studies that have been done in animals, and some of this stuff in animal is super interesting because you have you think of hummingbirds, which are an amazing example, that flap their wings super fast. And if you look at their breast tissue, it has the most mitochondria of any animal that's been measured. So same if you compare a turtle or a hummingbird or a jaguar or whatever the animal might be, you'll find that each animal will have a different number and quality of their mitochondria that is adapted to their specific way of living.
Right. What does our mitochondria tell us about us then?
I think that's where humans are classic. I think in the animal world, in that we're pretty good at everything.
Yeah.
But we can't compete with a jaguar or a cheetah on speed, and there's other endurance animals that we can't compete with. But I think there's no animal that's pretty good at both as humans are. If you look at like a lion, for example, they'll go out chasing their prey and have that intense exercise, and then they basically need to sleep all day. Whereas, like I said, humans have really good but not the best endurance capabilities, and have pretty good but not the best speed capabilities. And I think that that probably that versatility is has what's helped helped humans out of all animals to be able to adapt to basically all environments.
Yeah, so interesting. So even when we look at the mitochondria, it seems that humans are like more more flexible than other creatures that are more like focused on one single thing, like the cheetah, for example.
Yeah, I think, and that's a beautiful word, an excellent word, is a flexibility, and I think that's where, and it makes complete sense. For humans to be able to adapt in different environments, and having that flexibility where you can, if needed, be very good at endurance, or if needed, be quite fast, or if needed, be quite strong and have big muscles, then having that flexibility to adapt so as to be able to best cope with changing environments is probably a key to not only our ability to survive but our ability to thrive.
So interesting, David. It's been so fun talking to you. Before we end, like, I would like to know, like, if somebody would like to find your work or find like other stuff that you've done or your research group, for example, do you know, or can you tell us where people can find you and your work and or anything else?
Yeah, I mean, I think the social media is pretty big at the moment, and I haven't made it to TikTok or anything, but you can find me on.
Yeah.
That's that might be the next step, singing about mitochondria.
Exactly. Doing a dance with mitochondria, perhaps.
Yeah, well, I'll give that some thought. Maybe my kids have got some ideas.
Exactly.
But people can people can definitely find me on Twitter. And so my handle is at Blue Spot Science. And so there I'll post my latest research, but also the latest research from other people. Quite often it might be in the field of mitochondria, but just generally in the field of exercise for sport and health, I'll normally post things like that there. And I think that's probably a good starting point. If they go to there, they can also find links to my university webpage, and the university webpage also has my email address if anyone wants to contact me.
Yeah, perfect. Before we head off, like, what would you say? Like, what would be the take home message from today's conversation?
I think if I give two take home messages. I think one is that mitochondria are remarkably adaptable. So if you put them under stress, they will adapt and they improve. But if you remove that stress, equally they will return back to where they were before. So that sort of then comes onto the second point. So I think it's really important to get some sort of consistent exercise program so that you're regularly stressing the mitochondria. And I think the other thing I would say is that I think much like people, that mitochondria like variety. So rather than trying to hit them with the same exercise stimulus all the time, I'd be looking to try and get, if you're looking to try and improve your mitochondria, I'd be looking to try and get a mix of exercise. So mixing up some traditional low to moderate intensity endurance exercise with some high intensity interval training will probably give the best outcomes in terms of the mitochondria.
Perfect. David, it's been really fun talking to you, and I'm really sure that a lot of people really learned a lot, and you've been really, pedagogical, and you really taught us at the level I think that everybody can understand. So really big thank you for coming on and sharing everything you know.
It was a pleasure, Andre, and thanks for the great questions. I really enjoyed it as well.
Great. Okay, take care. Hope you enjoyed the episode. Friends, I really need your help. I'm trying to get the podcast out there. So I was wondering if you could help me by leaving a positive rating and a review on your Apple device or the podcast player that you're using, as well as subscribing to the podcast. That really helps getting the show more visible on iTunes and other players. And if you don't know how it's done, then YouTube has a lot of great videos, so you can search there. All right, that's it. Take care. This podcast is for general informational purposes only and does not constitute the practice of medicine, including the giving of medical advice. The content of this podcast is not intended to be a substitute for professional medical advice, diagnosis, or treatment.